Hi, I'm Mr. Richards, and today we're going to learn about arithmetic sequences as linear functions. Well, what is an arithmetic sequence? Well, it's a numerical pattern that increases or decreases at a constant rate, and that constant rate is called the common difference. In that first example, you can see we're from 3 to 5 to 7 to 9 to 11. There was an increase of 2. And then from 33 to 29, 29 to 25, 25 to 21, and 21 to 17, there was a decrease of 4. So the common difference in the first one was 2, and the common difference in the second one was a negative 4. In order to determine whether each sequence is an arithmetic sequence, the first thing we're going to do is look, okay, is there a difference that's common? From 15 to negative 13, there's a difference of plus 2. From 13 to negative 11, there's a difference of plus 2. And from negative 11 to negative 9, there's a difference of plus 2. So in example A here, yes, this is an arithmetic sequence since there is a common difference of 2. As my handwriting catches up here. In the second one, in part B here, from 7/8 to 5/8, that's a negative 2/8 or negative 1/4. From 5/8 to 1/8, that's a negative 4/8. And already I don't even need to determine that from 1/8 to negative 5/8 that I went down negative 6/8. And yeah, there's a pattern, but our answer to whether or not the sequence is arithmetic is no, since there is no common difference. So to determine whether each sequence is arithmetic, look for the common difference. In example A, there was a common difference of 2, so our answer was yes. In example B, there was no common difference, so our answer was no. Now we can also look for the next 3 terms in an arithmetic sequence by looking at the common differences. We're told this is already an arithmetic sequence, so we can assume that whatever the common difference we find, that will continue for the rest of the sequence. For the first one, from negative 8 to negative 11, we're going down 3, or negative 3 here. From negative 11 to negative 14, this is down 3, and negative 14 to negative 17, this is down 3. So for our next 3 terms, we can assume that this is going to continue to go down 3, and down 3. What are these terms? Well, negative 17 minus 3 is negative 20. Negative 20 minus 3 is negative 23. And negative 23 minus 3 is negative 26. So these next 3 terms are negative 20, negative 23, and negative 26. We can follow the same process in example B here. From 58 to 63, we are increasing by 5. From 63 to 68, we are increasing by 5, and from 68 to 73, we're increasing by 5. So once again, we can assume that for our next 3 terms, we're going to increase by 5, increase by 5, and increase by 5, which leads us to 78, and 78 plus 5 is 83. 83 plus 5 is 88, and those are our next 3 terms, 78, 83, and 88. So again, once we're told that this is an arithmetic sequence, look for the common differences and continue that for the next terms of the pattern. Now there is a way to come up with a rule to determine what the nth term of a sequence is. It's one thing to find the next 3 terms, but what if we want to find, say, the 85th term or the 90 millionth term? We don't want to do all that much counting. So here each term in an arithmetic sequence can be expressed in terms of the first term a1 and the common difference d. Well, again, our first term here we can write as A1, which makes our second term A2, our third term A3, our fourth term A4, and then our nth term will be AN. Now, in terms of A1 and D, with A1 being our first term and D being our difference, well, the first term is just the first term. We're not doing anything there. Now, with our common difference to get from the first term to the second term, we can take our first term A1 and add our common difference. In other words, if our first term was 7, we can do 7 plus, if our common difference, let's say, is 3, we can get to 10. Now, for the next term, for the third term, we would be doing something like 7 plus 6, or 7 plus 2 times the common difference, because this is the second time. So 7 plus 2 times that common difference would get you 13. And the way we can write that in terms of A1 and D is A1 plus 2 common differences. What about the third term? Well, following this pattern, this would be A1 plus 3 common differences, or 7 plus 3 times 3, which would get us 16. Now, what about the nth term? The way we're going to express this is our first term, A1, plus our our n minus 1 times our common difference. Now, why is it n minus 1? Well, for our fourth term, it was 3 common differences. For our third term, it was 2 common differences. For our second term, it was just 1 common difference. So for our nth term, it's not going to be n, but just n minus 1, since 4 minus 1 is 3, 3 minus 1 is 2, n minus 1 will be whatever that n minus 1 is. So in numbers, this would be 7 plus n minus 1 times 3. And here is the key concept in our box. The nth term of an arithmetic sequence with first term A1 and common difference D is given by this formula right here. Now, n is going to have to be a positive integer, but a to the n equals a1 plus n minus 1 times d. And this isn't a to the n, this is just an. Let's see how this works out in a few examples. So we have quite a few steps in this problem. We're going to use the sequence 1, 10, 19, 28, and we're going to try to write an equation for the nth term of this arithmetic sequence. Our first step in this is to find the common difference. So when we look at the numbers 1, 10, 19, 28, the common difference between these is plus 9. When we go to write our equation, we can use an equals a1, which is our first term, plus n minus 1 times d, with d being that common difference. So we don't know the an yet. We do know that our first term here is 1 plus n minus 1, and our common difference we found was 9. Now we need to simplify this. We're going to take this 9 and distribute it to the n and the minus 1. So that leaves us with an equals 1 plus 9n minus 9. Now we can simplify the 1 and the minus 9, And our final equation here is an equals, we'll write the 9n first, and 1 minus 9 is a minus 8. And we're going to use this equation now to find the 12th term of the sequence. So an equals 9n minus 8. If we're going to find the 12th term of the sequence, we put that 12 in for n right there. So an equals 9 times 12 minus 8. 9 times 12 is 108 minus 8. So our 12th term is going to be 100. In order to graph the first 5 terms of the sequence, we can go ahead and on the bottom we have 1, 2, 3, 4, 5, and these are going to be our term values, our n. In our results here, you can count up by 5 here, 5, 10, 15, 20, 25, 30. And now we can graph. Our first term was 1, so we can kind of go down here at 1, 1. Our second term was 10, so that's going to be 2, 10. Our third term was 19, so we can graph that at 3, 19 just below the 20 there. Our fourth term was 28, so a little bit below the 30. And our fifth term, well, we're counting up by 9, so our fifth term was 37, which is kind of right around this neck of the woods. Now we can use our equation that we wrote in step A, an equals 9n minus 8. And instead of putting in this 172 for n, we're saying we're looking for which term it is, so we can put the 172 in right there for the an. So 172 equals 9n minus 8, and now this just becomes a two-step equation. Add 8 to both sides, you get 180 equals 9n. Divide by 9 on both sides, and 180 divided by 9 is 20. So this is the 20th term. So a fairly complicated problem, but if you break it down step by step, first find the common difference, use this to come up with your equation, use your equation to find whatever term you're looking for and simplify. We can also use this to help ourselves make a graph. And then, not only can we look for, say, the 12th term, we can say, well, which term is a certain number? So there are a lot of different things we can do once we establish our equation. Let's look at one more example of how to do this. We're going to move a little bit quicker through this, but I do have one correction to make here. This 2 in the first term is not actually a 2. Let's make that a 7, so this actually works. Now, when we go to write our equation, the first step we're going to do is to find the common difference. So we have the 7, not 2, but 7, 12, 17, 22, and 27. And this common difference, which remember is just going to be our d in the equation that we're going to write, look for how it's increasing or decreasing. In this case, it's increasing by 5 for all of our terms. When we go to write our equation, we can always start with this equation here. A n equals A1, which is our first term, plus n minus 1, which represents whatever that last term is going to be, times our common difference. So when we go to make our substitutions in here, we don't know what an is. But we do know that our first term is 7 plus that n minus 1 times our common difference, which in this case was 5. Now we're going to go ahead and use the distributive property here in order to simplify. So an equals 7 plus 5 times n is 5n. 5 times that minus 1 is a minus 5. So our final equation here is an equals 5n. 7 minus 5 is a plus 2. I'm going to use that on the next few parts of this question. Find the 15th term of the sequence. Well, start with that equation, an equals 5n plus 2. We're looking for the 15th term, so that 15 is going to go in for n. That's going to be 5 times 15 plus 2. And 5 times 15 is 75, plus 2 is 77. So our 15th term, A15, is 77. Now before we graph, let's go to D. Let's see which term of the sequence is 97. So again, we can use our equation, an equals 5n plus 2. Go ahead now, and this 97 again is not going to go in for this n because we're not looking for the 97th term. We're looking for which term, so the n is going to stay, is 97. So 97 is going to equal 5n plus 2, and whatever our n is going to be is that term number. Solve this equation by subtracting 2 from both sides. 95 equals 5n. Divide by 5 on both sides. And 95 divided by 5 is 19. So this is then the 19th term. Let's go ahead and finish this problem off by making our graph. We can label the bottom here again, our first term, second term, third term, fourth, fifth term, and there's n. And here's our a to n. We can count by fives again, so 5, 10, 15, 20, 25, 30, 35. Our first term was 7, so that's kind of in between the 5 and the 10. Our second term was 12. Our third term was 17. Our fourth term was 22. And our fifth term was 27. So again, this is a lot of work in this one question. But to start off, look for your common difference. Start off with the shell of the equation. Make your substitutions in. Substitute in your first term. Substitute in your common difference. Those are the two things you know, your first term and your common difference. We then distributed in order to simplify this. We combined the 7 with the minus 5 to get a plus 2. And we wrote our equation. And then we can use this equation to find the 15th, 16th, whatever term we want by making the substitution in for the n. Or we could say, well, if we're looking for which term it is, substitute that in for the an, solve the equation, and you'll find which term a value will be. And just because we can also graph this information. Two more examples of this now. The arithmetic sequence 12, 23, 34, 45 represents the total number in ounces that a bag weighs after each additional newspaper is added. So there are some real life functions with this material. Now, we want to write a function to represent this. So once again, we can find our common difference. We have our 12, 23, 34, 45. Our common difference here is we're adding 11. So when we go to write our equation, we again still start with an equals a1 times n minus 1 times d. Substituting your first term is 12 times n minus 1 times the common difference of 11. Then distribute your 11 to the n and the minus 1, and this gets us an equals, forgot the plus signs, 12 plus 11n minus 11. Simplify it down to an equals 11n plus 1. And to write this as a function, we could write this f of n equals 11n plus 1. Now, to graph the function and determine the domain, let's go ahead and make a function table here, n and f and n. We have 1, 2, 3, 4, 5. And our values were 12, 23, 34, 45, and we can come up with 56 here by adding 11 again. We can then go ahead and make our graph with the fn there, the n down here. We can count by ones here again, 1, 2, 3, 4, 5. We can count up by tens on our left side, 10, 20, 30, 40, 50, and 60 as well. And 1 was 12, 2 was 23, 3 was 34, 4 was 45, and 5 was 56. So there's our graph, and our domain can be our x values. And our domain here, we're going to say we could have 0 newspapers, or 0, 1, 2, 3, 4, and so on. It just keeps going on forever. One more example. This arithmetic sequence, 22, 40, 58, 76, represents the total number of ounces that a box weighs after each additional bottle of salad dressing is added. So we have 22, 40, 58, and 76. Our common difference here is we're adding 18. To write our equation one last time this lesson, we'll start off with an equals our first term a1 plus our n minus 1 times our common difference d. So an equals our first term 22 plus that n minus 1 times our common difference this time of 18. Distribute the 18 to the n and the minus 1. an equals 22 plus 18n minus 18. Go ahead and combine the 22 and the minus 18, and an equals 18n plus 4. And again, we can write that in function notation. Fn equals 18n plus 4. So there's our function. We can once again graph this n and f of n by having 1, 2, 3, 4, 5. When it's 1, we had 22. When it was 2, we had 40. When the term was third, we had 58. Fourth term is 76. And if we add another 18 to the 5, or to the 76, for the fifth term we get 94. And we can also graph this. We can count our terms, 1, 2, 3, 4, and 5 for our term. And our result of the function, this time let's just count by 15s. 15, 30, 45, 60, 75, 90, and 105. We can graph our 122, and these are going to be rough estimates here. 240, 358, 476, and 594. And our domain here, once again, I pretty much had all of them, 0, 1, 2, 3, and so on. You could keep adding salad dressing until the box breaks, but we don't know what that is yet. So anyways, good luck.